Hello and welcome. This is Leon. Leon is a psychology graduate and he's interested in learning more about AI. He knows all about how our brain works, but doesn't know anything about how artificial brain works. So, in this video, we will explore the fascinating world of artificial intelligence together with Leon. We start by asking the question, how does our brain work? Our brain consists of many neurons. Neurons are the building blocks of our brain. They communicate with each other through electrical and chemical signals. Neurons can be connected to many more neurons. When a neuron is activated, it sends a signal to all the neurons it is connected to. Whenever a connection is more frequently used, it becomes stronger over time. This is how the brain learns new things. AI researchers have looked at this and tried to replicate this process in artificial neural networks. They have come up with something similar. It consists of two phases, phase 1 being the inference phase and phase 2 being the learning or training phase. Inference in this case means running the model and see what it will output. In podcasts about AI, this is a term that is used a lot. In the learning phase, the model is trained on a large dataset. For this example, we use a dataset containing handwritten numbers. During training, we feed these images to the network and the model will slowly update its parameters. Leon asks, so what are these parameters? Good question, Leon. Imagine again the brain that we had, with all the connections and neurons. And this brain is from someone who has learned a lot, and the connections are already built. A signal comes in. This, for example, could be light, sound, or a thought. For simplicity's sake, let's imagine this signal as an integer value between 0 and 100, where 100 means the signal is very strong. Let's see how the signal originally would go through the network. It flows through every connection, but gets weaker on the thin parts and stays strong on the thick parts. It ends up at this neuron the strongest. How research simulate those connections is by using weights, basically multiplication factors. This connection has a higher weight than this one. Let's see how this works in practice, by adding the weights to the first connection. Note that every connection has a weight, but we are only displaying two different ones right now. Let's also replace the neurons with circles to make it cleaner. Assume the input value is 50. That means that this neuron has a value of 50. The signal then travels through the connection. On the strong connection, the value is multiplied by 2.0, resulting in 100 at the next neuron. On the weak connection, the value is multiplied by 0.3, resulting in 15 at its target neuron. Now, the next layer is a bit more complex, because these have multiple inputs. Again, the value is getting multiplied by the weight, but this time it's summed together. Now let's get back to our dataset. This is a single image from the MNIST dataset. This image gets converted into numerical values between 0 and 100, representing the brightness of each individual pixel. These values are then fed into the neural network as inputs, where each pixel is directly connected to a single neuron in the first layer. From here, the signal propagates through the network, getting processed in each layer based on the learned weights, until it reaches the output layer, which provides the final prediction. Each of those 10 outputs corresponds with a prediction. In this case, we want the model to predict 4, so this one should ideally have a value of 100, while the rest should be 0. However, in the beginning, the weights are either 0 or randomly initialized, so the output values are not accurate. Let's initialize the weights randomly and see what the model will predict then. As you can see, the prediction is quite off. None of the outputs are close to the target values. This is where the learning phase comes in. During training, the model adjusts its weights based on the error in its predictions compared to the target value. Over many iterations, it learns to minimize this error, improving its accuracy. You can imagine this by thinking of the error as feedback. The first output neuron has an error of 46 because it predicted 46 instead of 0. It will send an update signal back to all the weights which are connected to the output node. The larger the error, the more the weights will update. This forms the basis of training a neural network. Whoa, that's so clear. Hey, I have another question. How do these neural networks work for large language models? Great question again, Leon. Large language models are essentially very large neural networks, often with billions of parameters. However, our previous network only had 10 outputs for digits 0 through 9, and LLM needs to output words and not per se digits. But there is a catch. Neural networks calculate with numbers and not words, so we need a translator. We call this process tokenization. Think of it as a giant lookup book, where every word is assigned a unique ID number. In large language models, however, most of the time, tokens are parts of words or single letters. These numbers are fed into the model, but not one by one. The model looks at the whole context in which these words are placed. The context is the sequence of all tokens so far. In this case, the context is Leon loves learning. It helps the model understand that Leon loves is likely followed by a hobby or a topic. The model processes this context through its layers and produces a probability score for every word in its vocabulary. It sees that the AI has the highest probability, so it selects that as the next token. And here's the magic. This new word is added to the context, and the whole process repeats. One of the main challenges in LLMs right now is increasing the context window size. Because as you can imagine, the larger the context, the more the LLM will understand of what the user wants. However, currently LLMs struggle with large context and they will drift off, as you sometimes may have noticed. Thank you for watching.